All right, we're gonna try to do L'Hopital notes, section 5.6, and see how this goes. So first of all, if you're using L'Hopital's rule, it has to be the indeterminate form, and the indeterminate form is one of these. So after you substitute in the number, which is always our first option when we're doing limits, if you get any one of these things, 0 to the 0, 0 divided by 0, 1 to the infinity power, infinity minus infinity, infinity divided by infinity, or 0 times infinity, or infinity to the 0. If you get any of those things, then you're eligible to use L'Hopital's rule, which can come in handy because it will allow you to find limits in some cases where you couldn't do it any other way. And in other cases, it's a lot easier to do it than the normal method that we had talked about in the first semester. Okay, so the directions for these first set of problems is use the techniques from the first semester and then do L'Hopital's. All right, so let's start with the techniques from the first semester. All right, so the first technique is to plug in the number, use substitution. If you plug that in, you're going to be dividing by 0, so that's no good. So then usually the next option was factoring, and this one is factorable. So we do the limit as x approaches -1 of 2x minus 3 and x plus 1 over x plus 1, and then those cancel. And then if you substitute in -1, you don't have an issue anymore, and it becomes -5. All right, so that was first semester. You might have to go back and look at those notes because we haven't done that in a while. That's the very first thing that we did in the fall. All right, so now we're going to do L'Hopital's rule. And L'Hopital's rule says if you have the indeterminate form, you can take the derivative of the top and the derivative of the bottom and then go from there. So we have to make sure L'Hopital's rule applies. So if you plug in -1 into the numerator, you're going to get 0. And in the denominator, you're going to get 0. And 0 divided by 0 is one of the indeterminate forms. So we can do L'Hopital's. All right, so L'Hopital says we're going to do the limit as x approaches -1, and we're going to find the derivative of the top, which is just 4x minus 1, and the derivative of the bottom is 1. And if you plug in now, there's no issue with the denominator. You come up with -5, and that matches our other answer, which it should. If it doesn't, something's wrong. All right, so that's L'Hopital's. Okay, so if you have, so I don't have a lot of room here, so I'm going to be erasing a lot of stuff. So if you need to rewind and pause it and copy some stuff down before I move on to the next thing, feel free to do that. Okay, so number 2, we'll do our old method. If you plug in 0, again, you're going to get, in this case, 0 on the denominator, but you're also going to get 0 in the numerator, which is, by the way, 0 divided by 0, which tells us we can do L'Hopital's for part B, but it also tells us we can't use substitution here. So if you remember, this was the sandwich theorem, and like I said, you may have to go back and look at the notes, but what we want to do is we want that to match the bottom. So if we got 4x on top, we need 4x on bottom. So if we do the limit as x approaches 0, and we have sine 4x, and then on the bottom, we're going to turn that into 4x by multiplying by 2. So that becomes 4x. But in order to balance it out, I got to multiply the top by 2 as well. So that I'm essentially multiplying by 1. And then this even though if I plug in, do substitution, I'm going to get 0 over 0 again. But we know by the sandwich theorem that that's equal to 1. And also you can look at it graphically. And so this becomes 2 times 1, which is 2. Okay, so that's the old method. We already know by 0 divided by 0 that we can do L'Hopital's. So let's do that. So we would have the limit as x approaches 0 of the derivative of sine 4x, which would be cosine 4x. But then we got to chain rule that, so stick a 4 out front. And then the derivative of the bottom, which is just 2. Okay, so if I substitute in 0 now, I'm going to get 4 times the cosine of 0. And the cosine of 0 is actually 1. So this becomes 4 times 1 over 2, which is 2. And that matches that, which again, it should. All right. I'm going to erase that. So if you need to pause it before I go on to number 3. Okay, number 3, the method from the first semester. Well, first of all, if I plug in infinity, I'm going to get infinity on the top, and I'm going to get infinity on the bottom. So I don't know what that is. Actually, I think we talked about this before, but if we haven't, most people think infinity divided by infinity is 1, and that's not necessarily true. It could be a lot of different numbers. There's infinitely many answers to that question. It just depends on how quickly it's going towards infinity. But that is definitely an indeterminate form, so I can use L'Hopital's when I get to part B for sure. The method that we used first semester was to divide everything by, sometimes it was x, actually most of the time it was x, but in this case I'm going to divide by x squared. So 2x over x squared plus 1 over x squared over 4x squared over x squared plus x over x squared. All right. So hopefully you remember that method. The reason why it's x squared instead of x is because you take whatever degree is the largest and you divide by that. So we have an x squared, so we're going to divide by x squared. All right, so on the top, 2x over x squared simplifies to just 2 over x. And I can't do anything with 1 over x squared. That's simplified. The bottom, 4x squared over x squared becomes 4. And then x over x squared becomes 1 over x. All right, so then we're going to plug in infinity. And if I plug in infinity, I'm going to have 2 divided by infinity plus 1 over infinity squared over 4 plus 1 over infinity. Okay, then from the first semester, we know that if we have a constant, doesn't matter what it is, if we divide by infinity, it's going to get really, really small, and essentially it's going to become 0. And if we take 1 and divide it by infinity squared, it's also going to be 0. On the bottom, we have 4 plus 1 divided by infinity, which is also 0. And so this becomes 0 over 4. And that is 0. That is not indeterminate. That's 0. We can have 0 in the numerator as long as we have something else in the denominator besides 0. All right, so the limit as x approaches infinity of this function is 0. Okay, so I'm about to erase this, and then we'll go to L'Hopital's. Okay, so this is part B. We already know it was infinity divided by infinity, so we can do L'Hopital's. So we'll go the limit as x approaches infinity. We'll do the derivative of the top, which is 2, and the derivative of the bottom is 8x plus 1. All right, so that's going to be, if I plug in infinity, 2 over infinity, and that is, if I take a number and divide by infinity, it's going to be 0, and that matches our first answer. All right, let's go to number 4. Okay, now the directions here say evaluate using L'Hopital's rule if necessary. So it's kind of your choice. If you see a method that we've already learned that seems like it would be good, like substitution or factoring and canceling, something like that, that can be done quickly and easily, then you should use that. And if you don't, and it's an indeterminate form, then L'Hopital's might be the way to go. All right. So I'm going to plug in, and if I plug in 2, even though it's approaching from the left, I still substitute in the number. I get 0 divided by 0. So that's the indeterminate form. So we can do L'Hopital's. So let's find the derivative of the top. So that would be 1/2 times 4 minus x squared to the negative 1/2, and then you'd have to chain rule this, which would give me negative 2x. All right, and that's all over the derivative of the bottom, which is just 1. Okay. So I could cancel that 2 and that 2, and I'm going to take that negative 1/2 exponent and bring it down the bottom. So this would be the limit as x approaches 2. Remember, we got to keep writing that. Otherwise, I got to take points off. So on top, I'd have negative x. And on bottom, I got 4 minus x squared to the 1/2 power. Okay, so if we substitute in 2 now, I'm going to get 2 on top, negative 2 on top, and on bottom, I'm going to be dividing by 0 again. So that's no good. So I'm dividing by 0. It is not a candidate for L'Hopital's because it is not 0 divided by 0. So I can't do L'Hopital's again. And actually, you can, as long as it is the indeterminate form, you can do L'Hopital's several times. Matter of fact, there was a problem on last year's final where you were required to do L'Hopital's, I think, 3 times in order to get the answer. But you just have to remember you can only do it multiple times if each time you do it, after you do the substitution in, it's indeterminate form. And this would not be. This would be 2, negative 2 over 0, and that is not indeterminate. All right, so we're kind of stuck here. But if you remember, when we were approaching from the left or the right, we could substitute something in that was close to it on the left side or the right side. So since we're approaching from the left, I would plug in 1.9. So the top would give me negative 1.9. And then on the bottom, if I plugged in 1.9 here and squared it, I would get almost 4. It would be something really, really close to 4. So when I subtracted it from 4, it would be really small. It'd be a very small number, and then I'd be taking the square root of that small number. And anytime we have a constant divided by a small number, then it actually grows and goes towards infinity. And in this case, since it's a negative, it would go towards negative infinity. So in essence, this limit does not exist. There is no limit. But also we can answer it, where does it go? And in this case, it's going towards negative infinity. All right. So that one we kind of used L'Hopital's and a technique from first semester. And don't forget, I could not use L'Hopital's again because it was an indeterminate form after I did it the first time. Okay, so let's go to number 5. Okay, so if I plug in 0, I'd get the sine of a times 0, which is the sine of 0. and the sign of 0 is 0. And same with the bottom, that would give me 0. And 0 over 0 is the indeterminate form, so we can use L'Hopital's here. So we'll do limit as x approaches 0, and the derivative of the top would be cosine ax, and then I would do the chain rule, and I'd get an a out front, and then the bottom would be cosine bx, and then I'd get a b out front. And then if I substitute in 0 now, I'd get the cosine of 0, and the cosine of 0 is 1, so this would be a times 1, and the bottom would be b times 1. So this would simplify to a over b, and that would be it. That's all you can do for that one. Okay, in that case, L'Hopital's was very handy. Made that problem a lot easier. Okay, so let's take a look at 6. If I plug in infinity, I'm going to get e to the infinity divided by 2, which is still infinity. And on the bottom, I'm going to get infinity. And infinity over infinity is an indeterminate form, so we can use L'Hopital's. So let's do the limit as x approaches infinity of, and then we'll do the derivative of e to the x over 2, which is e to the x over 2. And then this is like the same thing as 1/2 x, right? So I got to chain rule that, so that'll give me 1/2 constant out front. And then the bottom, the derivative of that is 1. Okay, so if I plug in infinity now, I'm going to get 1/2 times e to the infinity over 2. So remember, e is just a number. It's like 2.72. And we're taking that to an infinity power, which is going to be really huge, like infinity. And then I'm going to take infinity and divide it by 2, which is still infinity. And so this is going to be infinity over 1. And that is just infinity. It's not an indeterminate form. So this limit does not exist. But also, we know where it goes. So as we go towards infinity, this function is going towards infinity. All right, let's take a look at this one. So if I plug in infinity here, I'm going to get e to the infinity, which is infinity, infinity cubed, which is infinity. So that's infinity over infinity. So again, that is not 1. Matter of fact, we just did a problem where infinity divided by infinity was infinity. And it all depends on how quickly it's going towards infinity. In this case, it means the top is moving towards infinity much faster than the bottom. And it's taking over and shooting towards infinity, where the bottom is going much slower and can't fight that infinity on the top. All right, so let's see what this is going to be. So I'm going to do the derivative of the top, which is e to the x, and the derivative of the bottom is 3x squared. All right, so if I plug in infinity here, I get e to the infinity, which is infinity, over the bottom, which is also infinity. So it didn't really help, but we did get the indeterminate form again. So we could do L'Hopital's again. So we'll do the limit as x approaches infinity of the derivative of this now. So the derivative of that would be e to the x over, and then the derivative of this would be 6x. And if I plug in infinity there, that's going to be e to the infinity, which is infinity, and 6 times infinity, which is also infinity. Okay, so again, didn't help us, but we have infinity over infinity, so I can do L'Hopital's again. So I'm going to do the limit as x approaches infinity of the derivative of the top, which is this guy, which would be e to the x, divided by the derivative of the bottom, which would be 6. And that becomes e to the infinity, which is infinity over 6. And infinity over 6 is infinity. So the limit of this turns out to be infinity. Okay. Um, let's take a actually, I think I'm gonna stop there and, just because I don't want this video to be too long, and I'll finish this up with another video and share it. So